Hello everyone, I am Trupti Kapse. I'll be enlightening you upon some of the energy management techniques for SOC design. Some of them were previously explained by Pragya Jain. I'll be continuing it. First one is for reducing the switching activity. Lowering the switching activity is a very promising way of decreasing the power consumption. System level switching activity reduction can be categorized as follows. First, we can either turn off unused hardware modules, adjust data path, the bit width of buses and operational units in a system, trade precision for low power, compiler based instruction scheduling. Some of the basic strategies are clock gating and data path width adjustment. The best known technique for reducing the switching activity is clock gating. Clock gating essentially disables the clock to a circuit to save power by both preventing unnecessary activity in logic modules and by eliminating power dissipation on clock network. The bit width of data path and the size of memories strongly depend on the bit width of data. Providing more data path width for computation than required will consume more dynamic power and leakage power than necessary. Analyzing statically and dynamically requirements, unnecessary switching activity reduction can be achieved. We'll see some of the techniques for reducing switching activity. First is the dynamic power management. Dynamically reconfigures system to provide the requested services and performance levels with a minimum number of active components or a minimum load on such components. The fundamental premise for the applicability of DPM is that systems and their components experience non-uniform workload during operation time and that it is possible to predict with a certain degree of confidence the fluctuation of workload. There are two power reduction methodologies with ideal modes: voltage scaling with frequency scaling and clock gating. Second is the data path width adjustment. Processor based systems treat various data with different bit width. It is efficient in power reduction not only to determine data path width statically but also to control the active data path width dynamically. Static optimization, which adjusts data path width. Bit width analysis is performed to extract information on the required bit width of variables in programs and algorithms. For hardware design, using the result of bit width analysis, one can determine the length of registers, the size of operation units, and the width of memory words on the data path of a system to minimize the meaningless power consumption by the useless bits. Shorter registers and operation units reduce switching activity and the leakage of extra bits on the data path. Dynamic approach, which controls the active data path width. This approach is called value-based clock gating. Basic mechanism to reduce power consumption is operand value-based clock gating to turn off portions of memory, buses and arithmetic units that will be unused by narrow width operations. This optimization results in around 50% reductions in the data bus and integer unit power consumption. By applying this data memory, 80% power reduction can be achieved. Next is the compiler optimization. It uses instruction scheduling technique to reduce power consumption due to off-chip driving. Their technique reduces transitions on a data bus between an on-chip cache and a main memory, and as a result, power consumed by off-chip drives in the main memory is reduced. Next, we'll see the techniques for reducing the product of switching activity and a load capacitance. A major Next, we'll be seeing techniques for reducing the product of switching activity and a load capacitance. A major contributor to the system budget is the memory processor interface. The power dissipation of an external memory access is at least an order of magnitude higher than that of an on-chip access. For this reason, a lot of techniques for reducing energy consumption of the off-chip buses have been proposed. The basic idea is reducing the switching activities of hardware modules whose load capacitance is large, even if the switching activity of these load capacitance are increased. There are following three major approaches for reducing the energy required for the communication between a memory and a processor. First is the cache miss reduction. Since cache miss rate is associated with the number of off-chip memory access, reducing cache miss rate leads to a reduction of the energy dissipation for the off-chip memory accesses. The most straightforward way for reducing the cache miss rate is to employ larger cache memory on a chip. This technique is based on the fact that while a bigger cache consumes more energy per access, it can reduce the number of cache misses and a result can reduce the energy consumption for the off-chip accesses. Another approach to reducing the number of cache misses is a compiler-based approach. The idea is to modify the place of basic blocks, procedures, or global variables in the address space so that the number of cache conflict misses is minimized. This can significantly reduce the number of cache misses and energy consumption of memory subsystems. Next is the bus encoding. Bus encoding techniques reduce communication power by changing the format of the information in a way that the total communication power is minimized. The basic strategy is to reduce switching activity of off-chip buses by encoding data transmitted between a processor and a memory. Next is the code compression. An alternative approach to bus encoding is code compression. The basic strategy is to use narrow instruction codes for reducing the switching activity when the instructions are transmitted from a memory program to a CPU. On the other hand, there is much scope left to study on the source level design techniques which modify an application program in a way that power hungry hardware components are less frequently used without sacrificing performance, computational quality, and system reliability. Next, we'll be seeing techniques for reducing leakage power. For mobile or portable devices with a high standby to achieve active ratio, leakage current may be dominant factor in determining overall battery life. The three primary sources of leakage current are subthreshold or source to drain leakage current, which grows exponentially with lowering VT, increasing temperature, reverse bias junction to band tunneling current, and gate oxide tunneling current. Some system level methodologies related using these strategies are shown. Using high threshold voltage for non-critical paths, shifting the circuit to the low level mode, cooling high temperature parts, reducing the number of transistors. Next are the techniques using application specific hardware. The ultimate way for energy reduction is creating application specific integrated circuits that implement their algorithm directly in dedicated Fixed function logic. ASIC designers can also achieve good energy efficiency by starting with a processor core and then customizing the core to the needs of their application. Compromising point between high flexibility and low consumption has always been of interest. We can broadly categorize system level methodologies which satisfy high flexibility with low energy consumption. First is we can go for hybrid architecture, that is hardware and software partitioning for hybrid architecture that consists of a microprocessor core and a dedicated hardware. A hybrid architecture consists of a microprocessor core, a standard set of cores, and a set of application specific cores. The design goal using the hybrid architecture is to partition a given application into the microprocessor core and the application specific cores in order to minimize the total energy consumption. Hardware or software partitioning is the process of dividing an application into software running on a microprocessor and dedicated hardware. This approach is well established design methodology with the goal to increase the performance and to decrease the energy consumption of a system. Next, we can go for the configurable processors. A configurable processor core is a fully functional processor design that can be customized or expanded to meet the performance and energy efficiency needs of an application. Thank you.